This is 10.3, the beta lesson. And the alpha lesson was about the slope of a polar curve. The beta lesson is the area enclosed by one or two polar curves. Now, don't really worry about this. I think I'm going to explain this to you a little differently in the PDF. I just want to go through the example. So the area enclosed by a polar curve is the antiderivative of the limits from where to where of 1/2 r squared d theta. So the example we're going to go over is this. So this is the example that we're going to refer to in the PDF. This is what you're going to model to do the question we send you to. So if you were to graph this, r equals 2 times 1 plus cosine theta, that's what it would look like. And you want the area in there. So we're going from 0 to 2 pi. 1/2 r squared d theta. So you square the 2, right? You can distribute an exponent over multiplication. And you need a lattice to expand what's in the parentheses. Is that logical? See, the 1/2 is part of the algorithm. Then when you squared the 2 that was part of r, you got a 4, and the 4 and the 1/2 reduced to a 2. And then inside the parentheses, you have that expansion as per a lattice. So now what? Well, we got a problem with this. See, we can anti-differentiate, distribute the 2. We can anti-differentiate 2 cosine theta. No big deal. But cosine squared theta, we can't anti-differentiate that. Because if we said mu is cosine theta, and we have mu squared, we would need d mu, which is negative sine. And we don't have it. So we have to rewrite cosine squared theta in terms of the double angles. And again, I'm going to rewrite this a little differently than is on the PowerPoint, but you're just trying to get the idea. You can't just proceed from here. The third line, we have cosine squared theta, is a problem. So now what? Well, they reduce the 2 and they combine the 2 and the 1, give a 3. The constants. And you're just going to anti-differentiate that. So what'd you get? Well, 3 is the derivative of 3 theta. 4 cosine theta is the derivative of 4 sine theta. Cosine 2 theta is the derivative of sine 2 theta, ready? D mu. So you would need a 2 d theta. So you have to multiply by 1/2 to balance it. From 0 to 2 pi, which would give you that. Okay, so really, that you're dealing with sines and cosines. You can handle this. So on the PDF, first thing is, here is the question we showed you on Friday. This is the question from the end, problem 63, but you can do that now. Why? Because you're just trying to use the algorithm we just showed you what the area would be. which is 1/2 r squared d theta. Anti-differentiate that from the lower to upper limit. So what you need to do is you need to have the limits. That's what you need to be able to find. Okay? So take a moment, graph that so you can find the limits. So you can identify which is the accurate expansion. So what happened? Well, the graph's symmetric. So if you went from 0 to pi, what did we do? When you square this, it gets rid of the root sign, and you just have 3 plus cosine theta, 1/2 that from 0 to 2 pi. So instead of taking 1/2 that from 0 to 2 pi, if you just take that from 0 to pi, you would have the same answer, which was D. That make sense? So here is the question that we showed you on the PowerPoint. And here's the problem. The problem is this last term right here, cosine squared theta. So I did the problem a little differently than it was done on the PowerPoint. Because why? There is a PowerPoint in the last folder in Canvas that has the cosine and sine of alpha plus beta and double angles. So you can rewrite cosine squared theta. Well, let's do it this way. I rewrote that as 2 cosine squared theta subtract 1. Why? Because 2 cosine squared theta subtract 1 is the cosine of 2 theta. You can't just put a -1 in there, but I balanced it by putting a +1 there. So instead of doing the way they did it on the PowerPoint, we inserted this 0 here. -1 plus 1. We're going to group those constants. We're going to group the -1 with 2 cosine theta, 2 cosine squared theta, which we can rewrite as cosine 2 theta, which is the double angle. Then this one will be paired with that other constant. The 2 will give us a 3. So you got to the same place. The third line down here in that second cell is the same as the line on the PowerPoint. It's just a different way of getting there. But the issue is the double angles are not going away. You need to be familiar with these because you have to recognize that that's a dead end trying to anti-differentiate cosine squared theta without a negative sign. So it takes you to the same place, right? The area under the curve would be 6 pi square units. So I'll leave that up there. That's your model to go to problem 43. All right, so 43. There's the picture. Four plus 2 cosine theta, the quantity squared. From 0 to 2 pi gives you 1/2 r squared. Lattice takes you to there. Same problem, right? Distribute the 1/2, and you're here. 2 cosine squared theta is a problem. So you add a -1 and a +1. This 8 and the 1 gives you 9, and 2 cosine squared theta take away 1 gives you cosine 2 theta. Then what? Well, my mu is 2 theta, so I need a 2 d theta out here, and to balance that, I put a 1/2 out front of that integral. So the integral of the sum of the three terms is the sum of the three integrals. I only need the 1/2 on the last part, and it would take you to 18 pi. So you need to look at your work and look up there and see if your work diverged from what's up there. Well, because if I don't have that -1 and +1, right, this 2 cosine squared theta can't be anti-differentiated. You have a dead end because mu would be cosine theta, and you would need a negative sine theta in order to anti-differentiate it. So the only way to do that, to proceed, is to rewrite it in terms of a double angle. Example 7 is a calculator question. So what do you need for the calculator? You need the limits, and then you just math 9 it. Don't forget the 1/2. Okay? So problem 47 is a calculator question. So here's 47, which you don't need a calculator for. Ready? But you could. And then here's how Carson did it. So Carson said if I go from 0 to pi over 4, that's his picture of the graph. From 0 to pi over 4, the area on the curve is 2. Right? So this anti-differentiated itself because you had the 1/2 of the 4 reduced to the 2, which you needed for the d theta. Now, unfortunately, this is just one slide. On the PowerPoint, because these PowerPoints are a little dated. This, if we get an FRQ, is most likely what you would see. You would see the area enclosed by 2 curves. It's big R squared, take away little r squared. Not big R, take away little r, the quantity squared. Big R squared, take away little r squared, 1/2 that, from A to B, alpha to beta, d theta. Now, these questions are on the anticipated FRQ document under the polars. So they're more recent questions where they ask you for the area enclosed by 2 graphs. And back to the top, to remind you, here is the summary of what you're accountable for and what you're not accountable for. Slope, all those modes you're accountable for the slope. The length of a curve, function mode and parametric mode. The area enclosed by a curve, function mode and polar mode. This table is helpful, what you're accountable for and where you can find it in the textbook. And then what I meant to do earlier was my approach is to say the area of a circle, a sector of a circle. If you had a circle, the area is pi r squared. Here we get that. And you don't have the whole thing. You just have theta as a share of 2 pi. So if I distribute theta over 2 pi to this, the pi's reduce, and there's the algorithm. 1/2 r squared theta, where theta is d theta, the change, when you anti-differentiate that from the limits, which I think is easier to see it that way than in terms of the triangle that they were putting on the PowerPoint. All right. So that's all for 10.3 beta. That's all for chapter 10.